Okay, so here we're going to talk about a specific type of factoring, and this happens when we have a specific scenario called the difference of squares. So again, let's break down these words. Difference, anytime we see that, that's when we're talking about subtraction. So we need to see subtraction. If we don't, it's not difference of squares. Squares, what are we talking about? Not the shape, but the perfect square of a number. So that's what we're talking about here. Here are the first 10 perfect squares. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, and 10 squared. You don't have to have these memorized, but it's nice to be able to recognize your perfect squares. And this is only the first 10, right? They go up higher. 11 squared is 121, 12 squared is 144, and so on. So being able to recognize those helps you recognize when you potentially have the difference of squares. Again, it's not necessarily that you need to memorize, well, obviously you're not going to memorize every single perfect square because there's an infinite amount of them, but just recognizing at least the first 10, if not maybe the first 12 or 15, it's helpful. It's very helpful. All right, so let's look at what the difference of squares is. So if we have this scenario where we have subtraction of two perfect squares, hence the difference of squares, it's not just a clever name, then if we recognize that, we know this is always going to factor into this pattern of a minus b, a plus b, or a plus b, a minus b. I want to point out it does not matter the order in which we write the positive and the negative. But the point is, it's going to factor into two things that are exactly the same, where one of them is a positive and one of them is a negative. Also, those two things are the square roots of these two things. So I keep saying two things and so on. Let's look at an example here. So I've got v squared minus 25. V squared is obviously a perfect square because it is literally something squared. 25 is a perfect square. I know that because it's 5 squared. So I can think of this, and I don't need to write this. I'm just kind of trying to show you. This is v squared, and this is 5 squared. So in terms of the a and the b, in this case, v is a and 5 is b. So this is going to factor into v plus 5 and v minus 5. That's it. So again, the nice thing is if we can recognize that we have the difference of squares, then I know it's always going to factor into that pattern. So let's look at this. This was actually one of the examples we did on the greatest common factor video. So I'm going to go ahead and I'm going to take out the GCF first. That's 3y to the third, and then I'm left with y squared minus 16. So now here I can recognize this is the difference of squares. Right? I've got y squared, literally something squared, and then 16 is 4 squared. So if I recognize that, then it makes it very nice. I know that this is going to factor into y minus 4 and y plus 4, and then in this case I still have my 3y to the third as my GCF. That's the difference of squares. Again, the trick here is recognizing it. If you recognize it, it's really easy to factor. Okay, I want you to do some examples. So I want you to try all of these. Some of them are going to be a little more difficult than others. I believe that you can do it though, because I believe in you. Pause the video, try them, unpause when you're ready to check, or if you get stuck. All right, so for the first one, again, I broke it down here just so we can see that pattern a little bit better maybe. So we had 9n squared minus 16. Well, 9n squared is actually parentheses 3n quantity squared. And then 16 is 4 squared. So I know my a, I'm doing air quotes and you can't see it, and my b are 3n and 4. So this becomes 3n minus 4 and 3n plus 4. Boom, difference of squares. Here I have 4x squared minus 1. Remember, 1 is 1 squared, right? That's a perfect square. So 1 times 1 is 1. So here, this is going to become 2x minus 1 and 2x plus 1. Again, keep in mind if you the order in which you do the plus versus the minus does not matter. Here, this one's maybe a little more tricky because we have two variables, but again, they're still both perfect squares, so it doesn't change what we do. We just have to recognize the pattern. So x squared minus 9y squared is going to be x minus 3y and x plus 3y. Here, again, trying to step it up a little bit. So notice that this isn't x squared and this isn't y squared, but x to the fourth is still a perfect square. What times what? What times itself is x to the fourth? Well, that's x squared. So this, and again, I can write that out just if that verbal explanation wasn't that helpful. So 5x squared minus 4y squared. So then I get 5x squared minus 4y squared, 5x squared plus 4y squared. Here, stepping it up one more notch, I have x to the sixth. So that is going to factor into 8x to the third minus 11 and 8x to the third plus 11. So 11 times 11 is 121. X to the third times x to the third is x to the sixth. And 8 times 8 is 64. All right, so just adding on to our conclusion from last time, always look for a GCF first. If there are two terms, look and ask yourself, is this the difference of squares? Because if it is, then that's the pattern I want to follow. If there are three terms, then look and ask, well, can I factor it? How I know how to factor three terms? Nice job.